So let's have converse, contrapositive, and inverse. Um, we can form a new conditional statements starting with a conditional statement P implies Q. So in particular, there are three related conditional statements that occurs often that they have special names. The first one is the proposition Q implies P is called converse of P implies Q. We also have the contrapositive of P implies Q is the proposition not Q implies not P. Then we also have the proposition not P implies not Q is called inverse of P implies Q. Okay, so we will see that of these three conditional statements form from P implies Q, only the contrapositive always have the same truth value as P implies Q. So when two compound propositions always have the same truth value, we call them equivalent. So that the conditional statement and its contrapositives are equivalent. The converse and the inverse of the conditional statement are also equivalent. Okay. But neither is equivalent to the original conditional statement. So take note that one of the most common logical errors is to assume that the converse or the inverse of the conditional statement is equivalent to this conditional statement. Okay. So let's have an example. Okay. What are the contrapositive of the inverse of the conditional statement? The home team wins whenever it is raining. Okay. So it's not question mark, it is period. So because this statement, okay, the statement, the home team wins whenever it is raining, then, okay, we have first to identify what is the P and what is the Q. Okay, in the statement, the home team wins whenever it is raining, this would be, you have, this can be written as Q whenever P. So in this case, our P is uh, it is raining. So the P would be uh, it is raining, and our Q is the home team wins. So these are our statements. So in this case, our uh, our contrapositive is, okay. For our contrapositive, we could have, if the home team does not win, then it is not raining. So you have, if the home team, okay, does not win, then it is not raining. It is. So we have the contrapositive. If the home team wins, then it is not raining, because our P is it uh, it is raining, and our Q is the home team wins. Okay, so that's our contrapositive. So the converse of this is, our converse, we have, if the home team wins, then it is raining. So if the home team wins, then it is raining. Okay. So that's our converse. If the home team wins, then it is raining. Then our inverse, so the inverse would be if it is not raining, then the home team does not win. So these are the contrapositive, the converse, and the inverse of the statement the home team wins whenever it is raining. So remember that the given statement Q whenever P. Okay. So the P is it is raining and the Q is the home team wins. Okay. So let's have biconditional statement. So let P and Q be prepositions. The biconditional statement P, okay, if and only if Q, okay, this would be the symbol. So you have double arrow. Okay, the biconditional statement P, if and only if Q, is true when P and Q have the same truth values and is false otherwise. So biconditional statements are also called by implications. Okay, so this would be the truth table. Okay, so the truth table for P if and only if Q. Okay, note that the statement is true when both the conditional statement P implies Q and Q implies P are true and is false otherwise. That is why we use the word if and only if to express that this logical connective, okay, this is to express this logical connective and why it is symbolically written by combining the symbol double arrow pointing to the left and pointing to the right. Okay. There are also other common ways to express the biconditional statement. It is you could also have P is necessarily and sufficient for Q. Okay. You could have if P then Q and conversely. Okay. And then another common way of writing biconditional statement, you could have you have P double F, okay, or 2F Q. So if you have this symbol, P, even this can be this can be read as P if and only if Q. Okay. So you have this one. Let P the statement. Let the proposition P be the statement. You can take the flight, and let the proposition Q be the statement. You buy a ticket. Then, if we are going to write the P by P if and only if Q, okay, is the statement, you could have you can take the flight if and only if you buy a ticket. So here you could have, okay, you can take the flight if and only if you buy a ticket. So it means to say that if you buy a ticket, you can take the flight. And if you can take the flight if you buy the ticket. So that's how it is implies. Okay. So let's have the truth table of compound propositions. So let's have this one. Construct the truth table of the compound proposition. So uh, you have two compound propositions. P P or not Q implies P and Q. So for our solution, let us first uh, determine now the statements of P and or the truth values of P and Q. So for our solution, you have our P, okay, and we have our Q. Okay, so you have true, true, false, false. Okay, then you have true, false, true, false. Okay, so let's first have our not Q. So for not Q, okay, if the statement is true, then it is false. Then it is true. This is false. This is true. Okay. So if you have uh, P, okay, then you have this one. P or not Q, then you have this one. So if first is true, second is false, then it is true. If this is true and true, then it is true. Then false, false is false. Then false, true is true. Okay. Now let's have the P and Q. Okay. So you have uh, true, true, true. Then you have true, false is false. Then you have false, true is false. And you have false, false is false. Okay, so you have now these two statements. So you can now have this one. The statements implies. So this one, okay, so uh, true implies true is true. Okay, if you have this one, this is false. Then you have uh, if false, if the two statements are false, then it is true. Then if you have true, false, that is false. So this is now the truth values or the truth table of these compound statements. Okay, so let's have the propositional equivalence. An important type of step used in mathematical argument is the replacement of the statement with another statement with the same truth value. Because of these methods that produce propositions with the same truth value as a given compound proposition are used extensively in the construction of mathematical arguments. Note that we will use the term compound propositions to refer to an expression formed by propositional variables using the logical operators such as P or Q. Okay, so let's begin the presentation with the classification of compound propositions according to their truth values. Uh, truth values. So a compound proposition that is always true no matter what the values or what the truth values of the propositional variables that occurs in it is called tautology. A compound proposition that is always false is called contradiction. A compound proposition that is neither a tautology nor a contradiction is called contingency. Okay. So tautologies, okay, so that these are the truth table for the tautology and contradiction. Okay, so you have here an example. Okay, so if it is always true, then it is tautology. If it is always false, then it is contradiction. Okay, so tautology and contradiction are often important in mathematical reasoning. Okay, so that is very important. So let's have a logical equivalence. So the compound propositions that have the same truth values in all possible cases, okay, are called logically equivalent. Okay, so you have here uh, the compound proposition P and Q are called logically equivalent if P, okay, if and only if Q is a tautology. So you have there the notation. You have three dash. Okay, P three dash Q denotes that P and Q are logically equivalent. Okay, so the symbol three dash there is not logical connective, and uh, P logically equivalent Q is not a compound proposition, but rather it is a statement that P, if and only if Q, is a tautology. So you have there you have the by implication, uh, you have not by implication, that symbol, okay, this symbol. So this symbol, okay, okay, that symbol is sometimes used instead of you have three lines to denote logical equivalence. Okay, so you have there show that not P or Q, and not P and not Q are logically equivalent. Okay, so for our solution here, let's construct the truth table. Okay, so by the way, in determining the number of truth values, we have the formula 2 2 raised to n, where n is the number of propositions. So here, since we have two propositions, then we have uh, four four truth values in our table. So you have P and Q. So for our P, we could have true, true, false, false. Then you have true, false, true, false. Take note, okay, let me emphasize that our formula in determining the number of truth values would be 2 raised to n, where n is the number of propositions. Since there are two propositions here, then it should be 2 raised to 2. Therefore, there are 4 truth values. Okay, so let's first determine the P or Q. So true, true, that's true. True, false is true. False, true is true. And false, false is false. Okay, now let's have the negation of P or Q. So this is false, this is false, this is false, this is true. Okay, now this would be our the negation of P or Q. So let's have the negation of P. So our P is true, true, false, false. So that is false, false, true, true. Okay. So let's have the negation of our Q. So our Q is true, false, true, false. Therefore, the negation is false, true, false, true. Okay. So the negation of P and the negation of Q. So you have if false false, that is false. I am referring here. So if it is false true, then it is false. If it is true false, then you have false. And if it is true true, then it is true. As you can see, okay, these okay, these two columns, they have exactly the same truth values. Therefore, these two statements, okay, are logically equivalent with each other. Okay, so we also have other uh, logical equivalence here with their name. So you have this one. It is identity. It is in identity loss. Okay, P and the true. Okay, the equivalent is P, and P or false is P. Then domination loss. Okay, P or T. That's T. That's true. Then P and false is false. Idempotent loss, you have the P or P is equivalent to P. Okay. P or P, again, that's equivalent to P. Okay. So you have, if the statement you have the negation of P, that is P. Okay. Then you have P or Q. It is logically equivalent to Q or P. Then you have P and Q that is logically equivalent to Q and P. Now, you have if you have uh, P, the quantity P or Q or R, that is logically equivalent to P or the quantity Q or R. That's associative law. Or you could have also this one, okay, P and Q, the quantity P and Q and R is logically equivalent to P and the quantity Q and R. Okay, you also have distributive law. So you have P or Q and R that is just equivalent to the quantity P or Q and the quantity P or R. Then you could have P and the quantity Q or R. It is equivalent to the quantity P or Q and the quantity P, not and, or okay, the quantity P and R. We also have the De Morgan's law. Okay, the negation of the quantity P and Q is equivalent to negation of P or negation of Q. Then we have the negation of the quantity P or Q. It is just equivalent to negation of P and negation of Q. We could also have the absorption law. P or the quantity P and Q, that's equal to the P. Then P and the quantity P or Q, that's also P. Then we have the negation laws. P or uh, P or negation of P, it's true. And P and negation of P is false. Okay. Then we also have here another logical equivalence involving conditional statement. So you have, if P implies Q, it is just equivalent to negation of P or Q. Then if P implies Q, it is equivalent to negation of Q implies negation of P. Then you have P or Q. It is equivalent to negation of P implies Q. Then you have P and Q. It is logically equivalent to the negation of the quantity P implies negation of Q. Then you have negation of the quantity P implies Q is equivalent to P implies not Q. Then you have the negation of the, not negation, the quantity P implies Q and the quantity P implies R is equivalent to P implies the quantity of Q and R. Okay. Then you have the quantity P implies R and the quantity Q implies R. This is just equivalent to the quantity P or R implies P, the quantity P or Q implies R. Okay. Then you also have the other two statements. Then in the table 8, you have the logical equivalence involving biconditional statements. So that ends the presentation for this. That ends for this presentation. Thank you.